Yeah.
Good. Okay, great. So my talk will be about generous robots like language models need a little inference time human inputs. So I want you to imagine what happens when we have robot GPT where all the pre-training is done and we brought it home, right? Like ChatGPT will happily do things in the real world, sometimes making mistakes. And some of these mistakes it can fix by itself, but it has limited capability. So eventually, human has to sometimes come in and fix the robot mistakes. Uh, just like your AI coding agent when it tries to delete your whole repo, basically. So today, I hope to convince you that there are some natural communication interfaces in between the human and the robot GPT. Uh, so before we go there, we need a generalist robot. So we basically made one, but I don't claim we did everything. But I do claim that we can get pretty broad confidence by orchestrating good old robotics modules in a way with uh, VLM in a code as policy style. We show that with the proper tools, this framework can work for multiple platforms and perform much better than VLA methods. Uh, so the kind of task I want to show off here on the left is the robot taking an eraser and erase what's written on the whiteboard and try to stack the blocks in the order that's written on the whiteboard. And so it is able to do that. And on the right is a mobile manipulator trying to collect all the toys on the table. So you may wonder what kind of tools are available. I'll briefly go through them. We have look around, foundation stereo, Gemini pointing, SLAM, and then object memory in SLAM. And for geometric tools, we know language models are pretty bad at geometric tasks. So we have vector construction and rotation. For control tools, we have provable, like the planning framework. And there are some learned policies as well, such as GraspGen, which is a grasp generation model, and then Pi05 also. We also interestingly use Quen to determine when this Pi05 should stop. So when the VLM thinks Pi05 has a good chance of solving it, it will start it, and then Quen will decide when this will stop. Yeah, so I think this code and policy framework is pretty powerful. So we can show in this video, I'm showing more tasks, even more tasks with this robot. One thing to note that just like AI coding agent that can create, that can correct its own mistakes when there's a compile error, the agent we have can rewrite the code when the VLM sees something that's unexpected. So on my red note, I have asked me to do anything post for the mobile robot. So you can actually comment on what you want the robot to do and we'll do it at hand. Yeah. So I'd say we have a pretty robust and intelligent pick and place robot, physical agent that is able to take natural language and output low-level actions. And of course, I don't claim the work is done. There's so much work to be done on the skill level. Yeah, but at least we can start to think about how to interface and communicate with physical AI agents. So the first thing, which is my main complaint, is that this code writing and running takes a long time. You usually sometimes have to wait for 20 seconds for the robot to do anything at all. I think the main reason is that it has a huge prior and it has to extract information from a big model. So how do we get to use a smaller model for reasoning and planning so we can do things in real time? Our answer, like most people, is to just use human demonstration data and task relevant human demonstration data. we focus on try to create the smallest abstraction possible. So such an abstraction allows us to build real-time, if you will, world models of the consequence of the actions and then we can use search tools to find how to achieve the goal. So we borrow from the neurosymbolic and temp community to see if it's possible to learn abstraction from unsegmented data. Our key insight is that objects rest at meaningful locations after they move. So we can segment after they move, we'll find out which object is the moving object become resting with respect to. So such as the door moves about the hinge, the dish goes into the dish rack. For each trajectory, we use a VLM to figure out right here, to figure out which object is the reference frame for the moving object. Then we can summarize the meaningful relative pose and find out how the transition happens, and then also learn the skills needed to achieve that action. So almost like coming up with a PDDL domain, if you're familiar with that literature. And online, we can use symbolic search to recompose these skills, achieving compositional generalization. So here's a demo of data collection first, which we just collect play data, just randomly move things around in valid fashion. And then after 5 minutes of data, just 5 minutes of data, we can specify a new goal, such as a symbolic goal, such as lid on pen, banana in pen, block in pen, and then it will perform the necessary steps to achieve this goal. First, opening the lid first, and then put everything in. So these long horizon behavior also comes with error recovery. If it opens the lid and you close the lid again, it will try to reopen the lid. On the skill level, we also have error recovery because we are using a pretty special controller. We also show good result in RoboGasa, which has 85% success. Maybe let me give you one more second for the QR code. And so the policy class we use is called a linear parameter varying dynamical system. These are Gaussian mixture models that are super data efficient and guaranteed to be stable with just one equilibrium. So the left are the training trajectories. You can see it's just 10 trajectories and multimodal. And it picks the number of parameters for the model by itself using a expectation maximization algorithm. On the right are reproduced trajectory. You can see it's perfectly smooth and only has one attractor at the axis here. So summary so far, we have a generalist robot. We can use a tiny bit of data to improve its performance when the task is known, and we have demonstration for it in a manner that's robust to human disturbances. So how can we now address collaboration? So again, to emphasize, if robot GPT is going to be everywhere, then I think they should be allowed to in an environment that's around the humans. So connecting with the previous work, assuming we learned the PDL domain required to perform the task like previously, now we can allocate tasks in between the human and the robot. So I'm sure there's an optimal way to do that if you have a central planning agent assigning tasks for the human and the robot, but we want to let the human to have full autonomy and the robot perform the complementary task. And we find with egocentric view on a human, this helps with collaboration. So with the PDL defined, the possible actions actually in the world state is actually very limited. So maybe at a current situation, there's only pick tomato and pick mug is possible. So we input the frames of on the human, on the camera, on the human, and into a VLM, and let the VLM choose from the possible actions that have the preconditions satisfied. Then the robot assumes that action is done, and then we plan from there. So here's a demonstration of this AI to store simulator. Both agents actually know the goal, and upon human action recognized of pick tomato, the robot will go open the fridge so the human can put the tomato in there, and then after the robot open the fridge, it will go do something else. So we performed some user experiment, and we find this saves 36% of the time with respect to just human operating. And one quick other work is, what if the robot, what if you want the robot to do something that something different than what it actually plans to do? So we actually do physical human robot interaction as well. So here the robot is trying to pick up the gallon of water and try to move it onto the counter. And we use the most natural interaction method, which is just a gentle nudge. And upon the human push, the robot reduces the control gains and estimate the goal with a particle filter. And then that correction is actually translated back into something the algorithm understands. Yeah, so in general, I want to re-emphasize that generalist robot like LLM needs some human data to enable real-time and robustness. And it can use human-centric, human egocentric sensing to help with collaboration. And it can use human physical correction for intent recognition. Yeah, thank you guys so much. Here's my red note again and my website. And I'll just show some quick videos while I take questions if there are any. Okay. If not, we can move on to the next person. Oh, yeah, please.
Thank you for the point.
Yes.
About the egocentric sensing, can you compare the third view sensing? Is it different?
In a mobile setting, in a kitchen-sized environment, I mean, if you're talking about having a room full of cameras, like a motion capture system, I think that's going to be useful, and I feel that's the direction that I guess most companies are not trying to pursue right now, but I feel like it's possible. But if you have a third camera, a third view camera, I'm not sure how you're gonna keep looking at the human all the time and know what's it doing if it's turning its back at the robot, for example.
Hey, Simon,
Yeah, so
sorry to interrupt. I think we need to wrap up and leave some time for Frank.
yes. Okay.
Yeah, maybe do the, offline discussion.
Yes.
Yeah.
We can discuss offline. Yes.